Thank you very much for giving me the opportunity to talk here. So today I would like to talk about some results obtained in collaboration with Bruno Nachtergele, Hilaire Raz, and Robert Sims concerning a proof of Lieb-Robinson bounds for some type of anharmonic lattice system. So I'm afraid this has not much to do with Anderson localization, but two of my collaborators already gave talks in this program, so I didn't find a more appropriate topic. I hope it's still interesting. Okay, so let's start maybe by reviewing what are Lieb-Robinson inequalities, Lieb-Robinson bounds, in the original setting, which is the setting of quantum spin system. What is a quantum spin system? To describe a quantum spin system, we consider a finite set lambda, for example, a subset of the new dimensional lattice, and we define the Hilbert space H lambda by attaching to every point of lambda a finite dimensional space C and X, where you are supposed to describe the spin at site X. As I said, these are all finite dimensional spaces. Okay, now we need an Hamiltonian of this space in order to describe our model. The Hamiltonian in the most general form is given by the sum over all subset of lambda of some operator, well, in this case of some matrix phi of x, because everything is finite dimensional, where phi is a map from the set of subset of lambda into the algebra of observable, which in this case is very simply given by the multiplication of the space of all matrices of dimension nx. And we assume here that phi of x is symmetric for every x, and that phi of x is localized into the set x. So let's say the support of phi of x is contained in x. So what is the support of phi of x? We are going to say that the support of x, the support of an operator is contained in some set if the operator acts trivially on the rest, it acts as the identity on the rest of the points in the space. Okay, just matrices and x dimensions. Yes. But you can also think of it as being. Okay. So just to fix the ideas, because this is a very general setting, which sometimes it is a little bit maybe confusing. But the simplest example is and the most famous example is the Heisenberg model, where the Hamiltonian is given by a sum over all nearest neighbors of the spin at x times the spin at y. So here Sx, of course, is a vector with 3 components, and it's equal to the identity on every point. The only point where it acts non-trivially, of course, is the point x, and on x it acts by the Pauli matrices. Okay, so you see that in this case, the map phi is equal to 0 for all subset apart from the one which have cardinality 2 and where the 2 points are nearest neighbor. So this is how you describe this very simple model in this very general setting. Okay, once you have an Hamiltonian, you can start to look at the dynamics which is generated by this Hamiltonian. So the time evolution of the spin system. Let me use the letter tau t of lambda. Is a one-parameter group of automorphisms, which has the following form. You have to conjugate with the evolution on the left and on the right. And this is for arbitrary a in the algebra of all observable, and for arbitrary time t, can be negative, can be positive, of course. This is very clear. So Lieb-Robinson bounds now are bounds for the spreading of the support of local operators with respect to these dynamics. This is what Lieb-Robinson bounds are. So the question here which we ask is the following. Suppose that you start with an operator A at time 0, which is localized in some set X. You let it evolve according to these dynamics for some finite time t, and you want to ask, is it possible to find bounds for the support of this observable at time t, right? Well, strictly speaking, of course, this is a quantum mechanical system, so as soon as t is different from 0, the support will be everywhere, because it has small probability to go everywhere. However, it turns out that up to some exponentially small error, it is possible to approximate the evolution of a local observable by another observable whose radius only grows linearly in t. And this is an interpretation of this Lieb-Robinson bounds, which I would like maybe to write down in a more precise form. So this is the theorem. These are Lieb-Robinson bounds for quantum spin system. And it is as follows. So under appropriate assumptions on the map phi, more precisely on the decay of the map phi, maybe I will comment it in a second. There exist constants c, mu, and v such that the commutator between the evolution of A and B and then we have important part is now for every A, B in the observable algebra with support of A subset of X, support of B subset of Y. Like that. So this is the theorem. So what happens here? Well, if t is equal to 0, this is A, and you have to think that you have two observables, A and B, and they are localized on these joint supports. So assume that this is the set X, and here we have A. This is the set Y, and here we have the operator B, the observable B. Of course, since they act on independent part of the system, at time 0, they are going to commute. So the commutator is equal to 0. This bound tells us that as long as the time t is such that v times t is small with compared with the distance between these two sets, so dx and y. So as long as time is small compared to this distance, the commutator with arbitrary b, which is supported here, is going to be exponentially small in the distance between the two sets. And this, of course, this bound is only useful as long as this exponent here is negative, is positive. If it's going to be negative, then this bound does not tell us anything new, because the commutator is always bounded by 2 times the norm of the two observable, which is this part here, right? So, but as long as the distance is much bigger than v times t, this is very small, and this says that approximately the evolution of the operator of observable A is still did not reach the observable B, right? So if you want, this gives you an upper bound on the propagation speed of signals in quantum spin system. If you look at the system up to time t, then the observable A is only going to go up to distances of the order v times t. So with this distance here is v times t. Okay, the first proof of this theorem was given by Lieb and Robinson in 1972.
May I ask you a question?
Yes.
V would be what?
V is from the proof you're going to get some v, and
yeah, but to me, will it be the spin wave velocity? For
if you want to think in that terms, yes. I mean, it's at the velocity, of course.
Yeah, no, fine. But is it going to be the spin wave velocity for a Heisenberg
I think that in that case it's going to be that velocity, yes. But in general, I mean, especially for the theorem which I'm going to present later, it's going only to be an upper bound on on some physical velocity. It's not going to be the correct velocity. This is always.
So is this bound supposed to be? Is there a lower bound too?
No, that's not. So this is really the worst case scenario, right? So you have to look at the overall observables, and you can only give an upper bound. You don't. I mean, in principle, you can find observable which will remain there and will don't move. But of course, this depends a lot also on the interaction. I don't know.
The information is not specific enough.
That's right.
Yeah. Well, I meant in the Heisenberg chain. That's pretty specific.
Or Heisenberg.
Well, probably in that case, you would also expect to have a lower bound. Yes.
Would have some.
Must be a lower bound. Yeah, no,
Yes.
without more information, of course, that's you can just decouple the system or something.
That's right, and that's what I want to say. So you need some assumption on phi. Of course, you need some decay in phi. If phi is like in the Heisenberg model, phi is only a nearest neighbor interaction. So of course that's perfect. As long as you have a finite range interaction, that's all for arbitrary mu. And in this formalism, you can also look at interactions which are not finite range, but that decay sufficiently fast, exponentially fast, as the distance goes to infinity. Okay, so the first proof, as I said, was given by Lieb-Robinson.
So your estimate doesn't depend on the Hamiltonian, or what?
It depends, so these constants depend on the phi. C, mu, and v depends on the phi. I'm assuming that phi, for example, if phi is finite range, these and these are finite constant, and they are going to depend on the norm of the phi, as we will see in a second. So the original proof, as I said, was given by Lieb-Robinson in 1972. Recently, a new proof has been given by Nachter, Gale, and Sims. And the advantage of a new proof is that these constants are now independent of the dimension of the spin spaces, right? So the next question which one would like to ask in view of this improvement, if you want, is whether it is possible to extend this kind of estimate, this kind of inequalities, bounds, to system where at every point, instead of having a spin, a finite dimensional space, we have an infinite dimensional space. For example, in a lattice system, in harmonic or anharmonic lattice system, something like that. And
this is some kind of finite propagation scheme.
Yes,
right?
that's exactly
Basically, familiar with other
Well, maybe
systems.
I can comment on the spin wave. I've been thinking for a second. The spin waves for us have something to do with the ground state, right? An ordered ground state and low excitations of spin waves. But he's not talking about any ground state. He's just taking an operator norm. That somehow means to me that he's tracing over the entire Hilbert space.
yeah, but the spin waves should be the first excitations, if you want. So they are the lowest one. So the velocity which you should see is.
Yeah, but if you just bound the operator norm of the commutator, you're not specifically looking at the ground state. You're looking at the entire Hilbert space, everything that's going on.
Yes.
Particularly bounding the it could be that spin waves are propagating slowly, maybe.
Yeah,
There's high energy excitation which propagate much faster.
Yes.
And you have to bound those. So you will not get a very sharp bound on the spin wave velocity from looking at, I mean, possibly you getting not a very good bound on the spin wave velocity by looking at this object.
Yeah, so this is what you're saying is I could look at this at any temperature and it's totally temperature independent, right?
But spin waves, you also have fast spin waves, I guess, right? So, I mean, the question is it possible to go even faster than the fast spin?
I'm trying to give an answer to
Yes.
Christine's question. I think that right now we don't have a good, strong connection with spin waves. It's more general.
Yes. Okay, and well, as I said, the next question we wanted to address in joint work with Bruno and Robert and Hillel was to say if it's possible to generalize this estimate to system with infinite dimensional Hilbert spaces. Of course, the problem here is not the dimension of the Hilbert space, because as I said, now the constants are independent of the dimension of the Hilbert space, so that's not the problem. What the problem is that on infinite dimensional Hilbert spaces, you can also have unbounded operators, and then of course, if you take these bounds literally, your unbounded operator will make these constants C, mu, and V diverge to infinity as you look at as the norm of the observable goes to infinity. So the real question is whether it's possible to generalize this kind of estimate to system we define on infinite dimensional Hilbert space and described by Hamiltonians where some of the terms are unbounded operators. So this is the question we wanted to ask, and we can give a positive answer to this question, at least in some examples. So let me present our first example. So the first example of such system, let's call it bounded interactions. So in this case, we get the same generality as for spin system. Let me try to explain shortly what this is. So again, you take your set lambda, finite set lambda, subset of z to the nu, and this time you construct the Hilbert space by tensoring at every x a copy of L2, for example, like that. So this is an infinite dimensional Hilbert space. And then on H, you consider an Hamiltonian which has the same structure as before. So, and again, we are going to assume that the phi, phi of x is symmetric, and I'm also assuming that phi of x is bounded, and that support of phi of x is a subset of x. So this is the same thing as the spin system, right? Because the operators are bounded, so nothing changed, and there is no, to this Hamiltonian here, you can directly apply that theorem over there. And what I want to change is that now I want to add some unbounded part, but I want to assume that the unbounded part is completely local. So it's a sum over all points of some operator hx which only acts on a single point. You see, this operator here will not allow you to jump from one place to the other. It will only stay in the same place. And the theorem which we can prove for this operator here is exactly the same as before, and the constants are the same, which only take into account the phi. The constant will not depend on the h of x. So, as before, with the same c, mu, and v, which only depend on the phi, not on the hx.
So suppose you did add some something like a gradient of h squared or something like that.
This is going to come.
Yeah,
It's the next. This is the first example, the simplest example.
Well, we should have a picture. I guess we should imagine some oscillators.
Yes.
Every lattice point you associate some oscillator, and the Hilbert space is L2 bar, right?
That's right. Yes, this is the
prime example.
But the important thing is that the jump is not harmonic, because the harmonic jump, the potential would be quadratic, right? Instead, you take something which is linear. For example, let me write down an example.
So it is, physically speaking, it's coupled spring,
So it's this,
Unharmonic
maybe it's called the quantum rotor model or something like that. Is an example of this system. So example, you can take H. So for example, you can take an harmonic oscillator at every point. So you can also take a free particle at every point. This is fine. Qx squared. So here Px is just the gradient. And then you can couple them together. For example, nearest neighbor interaction. But I want to take a function phi, Qx minus Qy, where the infinity normal phi is bounded. Okay? So this is not, in the harmonic oscillator, this would be Qx minus Qy squared. That I cannot do with this method. As I said, later I will also consider something where this function is not bounded, but this is coming later. So let me start with this type of models here, where this part here is bounded. And maybe let me say something about the proof of this theorem, because maybe it is a little bit instructive. So the idea of the proof is to define the following function. Well, let's for simplicity take a simple model. Suppose that the Hamiltonian is just given by a, well, let's take something like that. A local operator, and then let's take only a nearest neighborhood interaction. And in this particular form, for example. Although this is not important, but just to simplify a little bit the notation. So this is the Hamiltonian, and then we define the quantity Ct of x as the supremum overall observable A supported in the set X of the evolution of A commuted with B divided by the norm of A. Like that. And the first observation which I would like to make is that, well, this quantity remains the same if you take it like that, and then here you, so remember tau t is the conjugation with the full H. Let me write this guy as H local plus the sum of the phi. So the H local is just the first part here. And then I want to factor out in the phase the effect of the H local. Sorry, this is H local. This commuted with B. Like that. See, why is it so? Well, because I'm taking the sup overall A whose support is in the set X, right? Now, if you take the operator A and you look and you conjugate with this local operator on the left and on the right, well, the support of this guy is going to remain exactly into the same set X. Because this guy, they do not change the support, they only act locally. So the support of this one is exactly the same as the support of A. The norm of this one is exactly the same as the norm of A. So this is exactly the same as this quantity here. Okay, and this is nice, because now we can take the second quantity. We can study this commutator by taking the derivative with respect to time. And you see immediately that introducing this phase helps you, because it helps you to get rid of the unbounded terms. Because what is the derivative with respect to time of this commutator? Well, remember that the tau t is just conjugation with a full Hamiltonian. Like that. So when I derive with respect to t, well, of course, here the Hamiltonian is going to come down, but here minus the local Hamiltonian is going to come down here. So what I'm getting here is a second commutator of the difference between H and H local and the local evolution of A. And then there is a factor of I or minus I, it's not so important, but it's there. So when I subtract from the full Hamiltonian the local part of Hamiltonian, I'm only going to see the bounded part, the phi part over there, right? So here I'm going to see only ht. Then I have the sum over all x minus y equal to 1 phi qx minus qy, commuted with this local evolution of A. Like that. Well, at this point, you see that, again, this guy here is going to be completely localized into the set X, where A is localized at the beginning. So I can forget this commutator for all x and y which do not intersect the set X. In other words, I can only sum here over all bonds x and y whose intersection with capital X, the set where A is supported, is not equal to 0. And I can forget about the other terms, because the commutator with the other terms is always equal to 0. Fine? Well, at this point, once I reduce the sum over all x, over all those bonds whose intersection with x is not empty, I can take the full evolution back in. Here there should be a minus, which I forgot. And I get the following double commutator. So overall both x and y whose intersection with x is not empty, of phi, well, let's qx minus qy. And then I'm going to commute this guy with this one, and at the end I commute it with b. I have two commutators. Okay? So you can re-express now this double commutator using the Jacobi identity as the sum of two double commutators, right? The first one is going to be something like, well, I commute first this with this and then the result with this, right? So the commutator, well, let's write it out once more. This commutator commuted with the new thing here. Like that. And then you have a second term where on the other end you have to commute this guy with the b, and then the result commuted with this. I'm not paying much attention about the signs, but something like that should be correct. And then with this evolved a. So I just use this Jacobi identity, which tells you that if you sum of a row cyclic permutation is equal to 0, so I can express one of them as the sum of the other two. And this is useful because you recognize in the first term, I get exactly the same quantity I started with, commuted with some other operator here, right? So I have an equation of the type, the derivative with respect to the time of some quantity, of some operator, is equal to I times the commutator of that operator with something else, with another symmetric operator. So if you don't have a second term, the first term would preserve the norm. It's just a Heisenberg equation, right? So it turns out that, well, let me do it here so I don't have to cancel. It turns out that this implies that when you rewrite this differential equation as an integral equation, you take the norm, you can just forget about the first term and just look at the second one. So in other words, it turns out that you can write the norm of this guy commuted with b is smaller or equal than what? Well, at time t equal to 0, we just have a commutator between a and b, which is bounded by twice the norm of a and b if the support of a and b overlaps. And otherwise it's equal to 0. So let me write this as a delta x and y, which means that if the two sets have a non-zero intersection, this is 1, otherwise this is 0. And then I have the integral over the time of, and then I have to take into account the second term, because this is the term which is going to modify the norm. So what do I have here? Well, I have a sum overall x, y, whose intersection with capital X is not empty, of, well, if you take the norm, I think you get twice the norm of A times the norm of this new commutator of e to the I ht phi qx minus qy e to the minus I h. It's actually not t, it's s because I'm integrating the derivative, right? So hs commuted with b. So, and the nice thing about this formula, you see, we start with something, we wanted to consider this quantity Ct of x, and we end up on the right side with something which has the same structure. So then you can iterate this equation. So you see, this is going to tell us that Ct of the set x is bounded by...
You just use a differential inequality now,
yes, you can do it like that probably, or you cannot just, you can just iterate, right? Because delta x and y, and then you have a sum of all terms which intersect with x. I mean, there are factors of 2, which I'm going to leave out. There is the norm of phi, which comes in because remember, the quantity Ct is always defined taking the supremum after dividing by the norm of a phi, and in this case, the norm of this operator is just the norm of phi. So it's phi times the integral 0 to t ds, and this quantity here is then Cs. The set changes, right? At the beginning, we have a set capital X, and now the set is just the bond between X and Y. Right? So you iterate it, and then you see that somehow you have to go, in order to obtain something which is not 0, you start from the set X, you have to arrive on the set Y by choosing this bond. So the first bond, XY, is this one. The next bond will have to intersect the first one, so it starts here, and then you have to find a path like that which goes from X to Y. And it's clear that you are only going to see non-zero contributions when you expand this thing up to, say, order n, if n, so the number of iteration, is at least as big as the distance between the two sets. And that's how you get the exponential decay in the distance between the two sets. Okay?
What does this say about this rate of?
Sorry?
I mean, but we still do not have any estimate for the rate of this.
Well, as I said, so what we are going to need is the... You're worried about the mu or about the v?
Both.
Okay, so that's correct. It turns out that in this case you can choose mu as big as you want. It doesn't matter. Yes, because this is a finite range interaction, and then, well, I mean, let's put it like that. Oops. Well, I'm not going to write down all the formula, but it turns out that this phi here is going to go into the v, because this is going to get, when you iterate n times, you're going to see the norm of phi to the power n, the time to the power n divided by n factorial because of the integration of the simplex, and then, as I said, so you're going to see something like sum overall n. N has to be at least as big as the distance between the two sets, so distance between x and y. And then I see something like norm of phi, some universal constant c. This is really like 2 or 3 or something like that, times the time t to the power n divided by n factorial. You see? And then here you can, for example, take out the d, so I get something like c to the phi times t to the power d divided, say, I want to say that n factorial is always bigger than d factorial times n minus d factorial. So here I get a d factorial decay, and then the rest just sum up to the exponent of exponential function of this form here. And then you see that if d is bigger than this quantity here, this is smaller than, so say that d is bigger than e to the minus mu, or e to the mu times this quantity here, you get as a precise, I mean, of course, if you want to choose the mu larger, you will have to choose the v also larger. So it depends what you want to optimize. If you want to optimize the mu or the v, you are going to do different choices of your parameters. But this is how you prove this kind of bounds. And again, let me point out, this is more or less the same proof as for the case of the quantum spin system. The only difference is that at the beginning, when we started, we had to factor out these two things here, because when you switch to this interaction picture, if you want, you get rid of all those terms which are unbounded, because when I take the commutator, you have to subtract from the Hamiltonian the local part, which is the unbounded part in this sense. So it doesn't matter what you add. If the terms which let you jump are bounded, then you cannot go faster than what you would for the spin system. Okay, this is nice, but of course, more interesting systems do not satisfy this condition that the jump terms are bounded. For example, as Tom was saying, harmonic system, lattice spin system, harmonic lattice systems were characterized by a function phi here, which is quadratic, so certainly not bounded. Well, in the case of harmonic system, it turns out that since you can compute many quantities explicitly, then you can also compute you can also prove this kind of theorem, at least for some special class of observable, using different techniques. So just by computing it out explicitly, essentially. Maybe let me say 2 words about the harmonic lattice system, and then I will switch to the more interesting anharmonic case. Okay, so this is the second class of system. Okay, in this case, let's take the set lambda to be the intersection of the lattice, so we have some dimension nu, so this intersects with this. So we have all points in a square if you want, in the higher dimension equivalent of a square. The Hilbert space, as before, is the tensor product of L2 spaces attached at every point. And the Hamiltonian is just an harmonic Hamiltonian. So we have, for example, something like this one. And then we have nearest neighbor interaction, which is quadratic. For example, like this one. Well, let's take a factor lambda here. Okay, so because this function is not bounded, we cannot apply the same theorem to this situation, right? So we have to do something new. But as I said, it turns out that in this case, since one can compute a lot of quantities explicitly, we can still prove this Lieb-Robinson type of inequality. And it turns out that in the case of harmonic evolution, it's particularly useful to work with while operators. So well, given a function f defined on the set lambda with complex values, we define the operator w of f as the exponential of, let's take like that, the real part of fx times qx plus the imaginary part of fx times px. Remember, px is just the gradient with respect to qx, and this is just a multiplication operator in my representation of the system. Well, while operators, they have a lot of very nice property. Well, first of all, they are unitary operators, so the adjoint is equal to the inverse, and is also equal to w of minus f.
So you're missing an I somehow, aren't you?
I am, thanks. Well, they are unitary operators. They intertwine, let's put it like that. They shift the position, the momentum operator by numbers. So this is probably qx plus or minus, I think, the imaginary part of f of x. And if you do the same with the p, you are going to find the same thing. So px w of f is px, I guess, minus the real part of f of x. And most importantly, they, well, I didn't write down, but they satisfy this while relation. So maybe I should write it here because this is equivalent to the canonical commutation relation. It is something like the imaginary part of the product between f and g, the L2 product between f and g. But the most important property, and the reason why they are so useful when dealing with harmonic evolution, is that the evolution of a while operator is again a while operator. Okay? So right? So if you take the harmonic evolution of w of f, this operator h is this h lambda is the harmonic Hamiltonian. This is equal to w of ft, where ft of x is just giving the convolution of f with some ht. Okay, so this is what is important for us, which means essentially that the locality property of evolution, in this case, as long as you look at the evolution of while operator, is directly related to the decay properties of this convolution function in the large X and large T regime. And, well, I didn't write down what this function ht is, so this is essentially the sum of overall momenta in the first Brouillon zone of the dual lattice, and then you have to take something like that, and the dispersion gamma of k in this case is something like omega square plus something like that, I guess, and there is a lambda. Well, I'm not so sure about this formula, but something like that should be correct. Okay, so using this representation, the theorem that we can prove is the following. If you take, well, suppose first take two functions, f and g, defined on lambda with complex values, and suppose that f is supported in x and g is supported in the set y. Then, when you take the evolution of the while operator w of f, again with respect to the harmonic evolution, and you commute it with w of g, there are some constants, which probably I will not write down explicitly, but the important thing is that you get like that. So you get this kind of commutator bounds. The commutator is going to decay exponentially as long as the distance is bigger than some harmonic velocity times time. And this is, you start with an operator which is localized in x, and you arrive at an operator which is localized at y, and then you get this kind of bounds. But the important thing is here, we use the fact that these are while operators, because otherwise we don't have explicit
If
forms.
not, you don't know what to do, or
Well,
I mean, you don't expect the same. Do you expect the same?
well, of course, if you have products of a finite number of while operators, you can do the same thing. But for general operators, I wouldn't know how to do, because this is really based on the fact that I can write this guy here is just w of ft, the other one is w of g. So when you take the commutator, because of these while relations, what you get is going to be these two things times 1 minus some phase, and this is just the product of ft with g. So essentially, to prove this bound, you just have to prove a bound on the product of these two functions. Of course, as the support is very far apart, for time which are short enough in that sense, you get something like this. Otherwise, I wouldn't know how to deal with the situation. Okay, so this is the harmonic case. It's fine, but still, it would be more interesting to do something in systems which are not, so to say, explicitly solvable. And this is the last class of system which I wanted to talk about. We can perturb the harmonic lattice system with some weak harmonicity and still get this kind of bounds. Now let me clarify what we mean by weak. So this is the number 3. So anharmonic lattice system. Well, the set lambda and the space are the same, but this time we want to take the evolution, which is given by the harmonic evolution, and the harmonic Hamiltonian, plus, and then we add some harmonicity. It's not so important what the harmonicity looks like. I mean, in this formula, please. Let me take something like that. I take it to be local, but it's not important. You cannot take something which is localized in some finite set. So what is important about this evolution is that the operator V is bounded, and actually that it has to decay sufficiently fast. So the precise statement is the following. Suppose that, well, V is a bounded operator, so the infinity norm of the function V is bounded. and then we also need to assume that it has a Fourier transform, and that this Fourier transform decays fast enough. This is not optimal, one can improve a little bit on this one. And you can also look at this, instead of looking at condition on V, you can look at condition on the derivative of V, because of course if you add constant, it doesn't matter, and actually this is just a simple way to write down this condition. So then we have the same statement. So if you take a while operator with wave function localized at x, you evolve it. Now I cannot compute what this is, because now we have an anharmonic evolution. So it's not like in the harmonic case where you know exactly that this is again a while operator. This is not going to be a while operator anymore. W of g. Well, this is smaller than some constant, and then we have the same exponential decay. And the interest, maybe to show to you that this is really a perturbation argument starting from that one, the velocity which we get is the same as the harmonic velocity plus, and then let's call this quantity kappa of v, plus some constant times kappa of v. So you see, we really don't use, I mean, maybe the potential v is, depending on how it looks like, you could even expect that we potentially improve the situation with respect to harmonic evolution. Well, for us, really, we don't see anything. The bound always gets worse, right? We only have to add some constant depending on the potential to the harmonic velocity, and this is the new bound. Okay.
Can you perturbatively see what kinds of these might enhance the velocity or decrease it? Can you tell from your perturbation theory what that should be?
No, I don't think that we can. We always look at the worst case scenario. I mean, it's always, okay, maybe in the last 10 minutes, maybe let me say something about the proof.
So the first condition, you want it to be bounded.
Yes.
And you want it to be somehow smooth, right? That's just a smoothness condition, I suppose.
Yes, you can look at it in that way, smooth, and it has to decay. Well, let's see.
Fourier transform. So
yes.
So that's a smoothness condition, I suppose.
That's correct. That's a smoothness condition.
Okay. Do you expect these things to be true if I put it in something like a quartic or?
Yes, of course. This is initially what we wanted to do is we want to look at quartic perturbation, which are physically the most interesting. I mean, it's also true that the quartic potential is used as an approximation, if you want, in the small distance domain. So you can really, I mean, if you have something which is look quartic here, and then you regularize it, I don't know, maybe like that.
Yeah.
Physically, it should not matter, and you should be able to apply this.
So cosine would be fine, right? I mean, cosine
yes.
would be okay.
Yes.
Is that right? Is that cosine?
No, it's not.
Why?
Is cosine okay?
What? I mean, square
Cosine
it's
cosine
okay.
of q.
Yes, yes.
That's okay.
Yes.
It's really bounded. I think about it. It's smooth, so I suppose that's what.
Yes. That's
Okay.
you have harmonic plus this. So
Yes,
quadratic
yes,
is always
yes.
there.
Quadratic is over. If you don't have a quadratic, then you can use the first term. The problem here is that you have a quadratic term, and that's when you have to do something. So the problem is that you have some jumping possibility. Okay, so maybe some idea of a proof. Okay. Well, the proof is based on interpolation between the harmonic evolution, which we know so well, and the full evolution given by this operator, generated by this operator h, which we don't know so well. So the idea is that we define, let's take it like that, h harmonic, t minus s, and then you have w of f, e to the minus a, t minus s, like that.
You want to use the same trick you did last time, right? Or not?
But it's a little bit different because now I'm interpolating. So in the other case, I just removed the
Yes.
switch into.
Yes.
And in this case, I'm interpolating between this, and I'm going to use very much. I mean, this guy here is of course not localized, but the idea is that I know it very well, so I can use this fact. So note that if you take s equal to t, you have a full evolution. If you take s equal to 0, you have harmonic evolution, which is not, right? So what you would like to do is you want to write g of t as g of 0 plus the integral of the derivative. That's the same trick, yes. And then you compute just what is the derivative of this guy. I mean, sorry, I have to commute with this one, where there are two g's, so let's call this function, I don't know, w of s and w prime of s. So when you derive with respect to s, here you really get just the difference between the full and the harmonic evolution, which is the same thing as before. In our case, this is the sum of this potential. So maybe let me write it like that. Sum over all x of v of qx commuted with the harmonic evolution of the while operator, which I know is again a while operator, an evolved while operator. And then it's e to the minus I hs w of g. Right? So this is the difference between h and minus h tilde, which comes here, and then you have to commute this guy with this guy here, which is the evolution of the while operator, and so you get this nice formula here. Okay, now let's take the sum over x outside. So we have a commutator between v and the while operator here, where we can write this guy as hs. Well, let's pull out the while operator if you want, ft minus s. So this multiplies what? Well, if you pull out w, here I have to multiply back with w star of ft minus s, v of qx, w of ft minus s, minus v of qx. And then I have the same thing as before, so I have the full evolution commutator with w of g. I just pull out one of these w's. W times w star is equal to 1, so the first term is v times w, and the second one is minus w times v. So just a commutator. Okay? So what is, when you take, as I said before, when you conjugate with while operator from the left and on the right, what you do is you are shifting the multiplication operator q of x. So this is the same, actually, as the sum over all x ft minus s, and then we have the difference of two terms. The first one is v of qx plus, and then I think it's going to be the imaginary part of f, the evolved s at the point x, minus v of qx. I just rewrote this thing here like that. And this you multiply with e to the minus I hs, and you commute with w of g. Okay? So if I want, I can also reintroduce here the e to the minus I hs times e to the I hs. Just multiply with the identity, of course. And then you see that we have a commutator of w of g with a product of two operators. The first operator is this guy here. The second operator is this guy here. Of course, this is the same as the sum of two parts. The first term, I take the first operator out on this side, and then I commute the evolution of this difference. Well, let's call this delta v of x with w of g. The second term, on the other end, I pull out this difference here, and I have sum over x, and I have the commutator of w of ft minus s, w of g, times e to the I hs delta v of x e to the minus I hs. Well, let's see the first term here. W of ft minus s is the same as this evolution here by definition, right? So the first term here is again the same thing we started with. This is the function w of s times some new operator here. Again, this operator is not going to change the norm. So if you write w of t as w of 0 plus the integral, and then you take norms, well, you will not see the effect of this term. In a sense, you can factor it out and you put it in the exponent as we did in the beginning if you want. So in other words, what matters is the first term. And the first term, I mean, I have something which is a bounded operator here, and then I have something like that. And the idea is, again, I would like to iterate this bound which I'm going to get. But how can I do it? The difference of the two potential in general is not a while operator. So I started with a while operators here and a while operators here, but here I have a while operators here, I have something else here. So what do? Well, I assume that V is nice, I expand it into a Fourier integral, and then e to the I q times this thing here, that's going to be a while operator.
That's where you need
Yes.
the smoothness.
Yes, that's right. So when we're going to take, as I said, the function w, and unfortunately I changed g to w, I didn't realize that w is also a while operator. So the function at time t is what we are interested in, this commutator, and I take its norm, is bounded by its value at time s, which is just the harmonic evolution, the harmonic commutator, which I know how to bound. So this is h t w of f plus, and then I have a sum over all x's. I take the integral from 0 to t ds. Let's go back here. Let me expand, as I said, the potential into a Fourier series over kappa, v hat of kappa, and then I'm going to see the commutator of e to the I h s. So what do I have here? I have e to the I q, so let's call it e to the I kappa qx, and I can also pull out, because I have a difference of two terms here, but when I put it in the exponent, the difference is just going to be e to the I, this guy times kappa, and here it's 1. So I think it's going to be times the imaginary part of f t minus s of x minus 1. And you take the absolute value of this number. This is a number, okay? When you expand, after you expand this guy into Fourier series, the only operator part of it is the e to the I kappa times qx. And this is going to sit here. E to the minus I hs commuted with w of g. Okay? And then here, of course, you can bound this one by kappa times the imaginary part of f. And then what do we know? Well, we have a sum over all x in lambda, right? But let's check. So this guy here is going to be very small. So this is x and this is y, right? And f of t minus s is the evolution up to time t minus s of something which initially is localized in the set x. So if the number, if the point here, small x, is very far from x, this is going to decay exponential, right? On the other hand, if I'm close to x, this is not going to decay exponential, but then I still have a full commutator here because I'm still close to the initial thing. So iterating this kind of bound, again, you can prove at the end. Of course, and it's important to use that for the first term, we know the exponential decay. So in this case, the exponential decay, and then you can just iterate the same equation, and you get to this estimate here. Okay. So I probably will stop here. Thank you for your attention.
Some questions or comments?
So what are challenges remaining basically unbounded operators, right?
Sorry?
I mean, what are main challenges remaining in this business? What you mentioned?
It's unbounded operators, yes. Now I have I mean, in all this system which I talked about, part of Hamiltonians was unbounded operator.
So does one expect, I mean, if I put in a q to the fourth, I don't expect any, I still expect the same behavior,
Yes.
right?
Well, this is very strong in the sense that you take the norm here. Maybe if you have q to the 4, then you have to take some weaker statement. Maybe the norm statement is not going to be appropriate for the
I see.
q to the
Yeah. So you work only with the norm. With
Yes,
the norm.
yes.
It's also probably partly related to
Yeah.
Martin's remark that
Yes.
you cannot project on ground state
Yeah.
close
You
to
can
ground.
imagine some very crazy state
Yeah.
that would somehow use
Yep. Yep.
the rise of the potential and
Right.
do something absolutely bizarre. It's could
I
happen.
mean,
I
this
suppose.
So you
this
can't-
cannot happen if, as long as the jump, so the part which is not local is bounded. Then in that case, everything remains bounded. It doesn't matter what happens in the vertical direction. If this if you want this phi effect, which allow you to jump from one side to the other, is bounded, then everything remains bounded. But as I say, I mean, if you have a quadratic coupling between neighbors, then it's not so clear, it's not so transparent that what happens in the vertical direction is not going to affect the propagation in the horizontal direction.
Now, in nonlinear wave equations or things like that, you also get, of course, finite propagation speed. So,
Yes.
so it comes out instantly because of,
Of
well, at least if you have
of the
you
speed
know,
of
Huygens
light.
principle and things
Yeah.
like that.
Yes.
It just
Yes.
comes instantaneous. Of course, you have a lattice here, and you can't expect to have
Yes.
anything like Huygens. You can maybe have an approximate Huygens principle, but not
Yes.
not a real one, and
Mhm.
so you're fighting against that.
Yes, I think that's
not only Schrödinger wouldn't have a Huygens principle either. So,
No, that's right.
but also, see, I think what I would find interesting is if there were any kind of lower bounds.
Yes.
Is there any mathematical or physics literature? So generally speaking, it can be quite non-trivial. In nonlinear wave equations, it can be quite non-trivial to get a lower bound, and you typically need some
kind of
you can't have any inhomogeneities in your system.
Yes.
Then you'd be talking about localization and delocalization. But if you just have nonlinearities and their translation invariant, then there are theorems like Morowitz theorem and other things.
That's right. Yes, I mean also in the Schrödinger picture, it's
it should decay even in the presence of nonlinearity under good circumstances.
So in the Schrödinger picture, you have this type of Moore type of estimates,
Yeah,
which give you
yeah.
some minimal velocity of minimal escape velocity if you want.
Yes.
But these are, I mean,
So none of those ideas are applicable here. I guess.
I'm not aware that they are applicable. I mean, I never tried actually, but I don't.
I mean, Martin's point may come back again to this question, you know.
Yes.
But somehow I would imagine that for something simple like quantum Heisenberg,
Yes.
let's say,
One should be able to
one,
get some.
one should be able to establish some kind of minimum propagation speed, or something like that. I don't know exactly what one should have. There are problems like that even on the lattice. Actually, it's a much more subtle question than it is in the continuum. For reasons you can imagine, the lattice gives you extra troubles
Because of all this geometry.
Yeah, because of the geometry of the lattice. So that in the propagation speed, if you just take nonlinear wave equations on the lattice, you will not get the same propagation speed as you go in the continuum.
Yeah.
The continuum is nice because it couples you up to the high momentum modes, and the lattice your momentum modes
Yeah.
are cut off,
Mhm.
and you don't see the same physics. And so I don't know how easy it is. So there may be another formulation.
I mean, for the harmonic case, I'm confident that you can do it because you can compute everything.
Yeah.
But otherwise, I don't really know.
So are there results of that kind? Anybody know about the spreading of the wave packet? I mean, it's sort of a basic question, right? You want to know that these things do spread, and there are no traps somehow. You're not stuck in some.
I mean, the only thing that I'm aware of are these results. If you have
There
this
could be
system.
solitons and other things. That,
Yes, but if you are orthogonal to this thing, then you should.
which will prevent you from spreading, and those do occur on the lattice in
I see.
certain systems, but in the continuum they're pretty hard to arrange.
I see.
Any other comments or questions?